Hi everyone, my name is Dr. Jonas Lukaczek and I'm going to present Cinema Darkroom, a deferred rendering framework that enables high-fidelity post-hoc visualization of large-scale datasets. For example, the image you see here in the title slide was completely generated just based on two depth buffers, one for the isosurface and one for the extrema, where the entire lighting, edge highlights, color mapping, and depth of field were computed in image space. In a nutshell, Cinema Darkroom flexibly renders geometry buffers that have been stored at simulation runtime in a cinema database. These geometry buffers can contain any generic shading information, such as depth buffers and data textures. Cinema Darkroom then passes these geometry buffers into a flexible shading network that features screen space ambient occlusion to approximate lighting, screen space depth of field to enhance depth perception, image-based silhouettes to highlight edges, and many more image-based shading techniques, where the user has complete control over the creation of the visualization pipeline through a user-friendly node editor. The system is also designed to be easily extendable by, for example, adding custom shaders with minimal overhead. But before we dive deeper into Cinema Darkroom, I want to give you a quick tour of the history of image-based in situ visualization which motivates our work. Our system is rooted in a core dilemma of high-performance computing, namely that the capability of computing hardware grows much faster than the capabilities of the storage and network infrastructures. So supercomputers can produce unprecedented amounts of data, but due to bandwidth constraints, it is infeasible to transmit all that data through the network or store it to disk. So we need to carefully select what we push through the I/O bottleneck, where the overall goal is to store as less as possible while at the same time enabling as much flexibility as possible during post-hoc exploration. Of course, a visualization is an essential part of post-hoc exploration, so one central question becomes what to store in order to visualize the simulation state after it is no longer available. Ahrens et al. Proposed to solve this problem by generating visualizations at simulation runtime and then storing them in a so-called cinema database. Their approach is based on the rationale that no matter how big the data is, at the end visualization happens on a viewport with a fixed number of pixels. So they propose to store image samples of the parameter and visualization space, where the parameter space consists of different time steps, ISO values, persistence thresholds, and other analysis parameters, while the visualization space consists of camera positions, clipping planes, transfer functions, and other rendering-related options. The resulting image databases are several orders of magnitude smaller than the data they are derived from, and they can be interactively browsed post-hoc along the sampling axes. Cinema database explorers, such as the one shown here, can therefore emulate real-time interaction with datasets of any size by simply snapping to the next available sample point. However, the flexibility of post-hoc exploration is obviously limited to the samples stored in the cinema database. Though this approach requires a lot of foresight about suitable samples, especially in regard to the visualization space, like where cameras should be placed, what color maps should be used, how to light the scene, and so on. Every decision made in this step has a significant impact on the quality and flexibility of the post-hoc exploration. The concept of deferred rendering can mitigate this problem as it decouples the information required for shading, such as depth buffers and data textures, from the shading itself, in which one needs to determine suitable color maps and lighting settings. In the context of in situ visualization, deferred rendering can be used to only store the underlying shading information, collectively referred to as geometry buffers, in the cinema database, and postpone final shading to the post-hoc exploration phase, at which point visualization parameters that were not known a priori can now be interactively adjusted. The latest cinema specification provides guidelines on how to actually store geometry buffers in a cinema database. On a personal note, I still have the impression that many people who could definitely profit from using cinema databases are still hesitant to integrate them into their projects. I guess the primary reason for this is that they think cinema databases require a lot of overhead and special data formats, but cinema databases are deliberately kept as simple as possible. In fact, a cinema database is just a folder with the extension .cdb that can contain any kind of data product, for example JPEG images, VTK files, raw binary data, and so on. The only special thing is that the folder has to contain a data.csv file that has a column named file that records the relative path to all data products, and any number of additional columns that record associated sample values of the data products, such as their corresponding cycle time, object ID, and whatsoever. This CSV file is consumed by database explorers to understand the content of the database and the axis on which it can be browsed. The example database on this slide just contains 4 geometry buffers in the form of VTK image files, where each buffer is associated with a timestamp and an object. That is all there is to create a cinema database. Of course, you can make the structure of the database as simple or as complex as necessary for your project. For example, if you want the user to be able to rotate the camera, then you need to store geometry buffers for different camera angles and record for each buffer the corresponding camera angle in the CSV file. Any intelligent cinema explorer will understand this and then allow you to rotate the camera with your mouse. The topology toolkit actually features a powerful cinema database adapter and even features a VTK filter that can generate geometry buffers. This filter is called TTK Cinema Imaging and takes 2 inputs, a triangulated object that is supposed to be depicted and a sampling grid that records the camera positions and calibrations. The filter will then generate for each camera a geometry buffer that contains a depth buffer and a data texture for any array stored on the input triangulation. In advanced scenarios, the geometry buffers can also store additional information, such as ambient occlusion, motion blur, or light factors. However, as I will show in the rest of the presentation, the depth buffer alone often suffices to produce high-quality visualizations that are on par with path tracing. The database adapter can then be used to store and later retrieve the geometry buffers. For more details on how to use cinema databases and TTK, I refer you to the TTK webpage. Now that we know why and how to create cinema databases containing G-buffers, we revisit the front end of Cinema Darkroom that processes these databases. The main interface element is a common node editor, just like the one used in Blender or in Vivo, which enables users to create a pipeline graph. Individual nodes of the graph correspond to shaders or other filters, where input and output parameters are shown via ports. The output of one filter can be used as an input of another, which is indicated by an edge. The pipeline follows a push model, thus as soon as a new input value is available, the filter updates its output, which then triggers an update of filters that use the updated output as an input, and so forth. Values of unconnected inputs can also be adjusted via widgets that are shown right next to them. The interface also contains a render view that shows the output of a selected filter. Regarding its actual implementation, the front-end is completely written in JavaScript and WebGL, where the front-end can either directly import a cinema database or connect to a ParaView server via a WebSocket to retrieve G-buffers. G-buffers and intermediate renderings are then passed along the network as frame buffer objects. If a filter corresponds to a shader, then its inputs are automatically passed to the shader as uniforms. Cinema Darkroom features several image-based shading techniques, from rudimentary operations such as color mapping and scene compositing to advanced shading effects such as screen space ambient occlusion to approximate global illumination and screen space depth of field to enhance spatial perception. Moreover, one can easily add new techniques to Cinema Darkroom with minimal overhead. In the simplest case, developers just need to create a single JavaScript file in which they inherit from the general filter class, supply a fragment shader, and specify the input and output parameters of their filter, where the input parameters are automatically passed as uniforms to the fragment shader. Something I'm really excited about is that we are also currently porting everything into a ParaView plugin. Actually, all image-based techniques are already converted into VTK image data filters, but ParaView was never designed to build complex pipelines, which makes this process rather painful. So we are now working on a separate plugin that will provide a node editor for ParaView, in which it will be as easy as in the web-based front-end to build shader networks, with the additional advantage, of course, that you can also use it to design any pipeline. Okay, now let's have a look at some results. In the simplest use case, one just needs to apply post-hoc color mapping. Here you can see a simulation of a two-material inertial confinement fusion problem in 2D that was simulated at the Lawrence Livermore National Laboratory. Instead of storing the raw simulation data, their scientists generated a highly time-resolved cinema database consisting of over 2,000 scalar images with a resolution of 2,048 squared pixels. This database is roughly 20 times smaller than the original simulation data, and that is without compression. Of course, prior to the simulation, it is not clear what color map will be most suited to visualize the data, so this needs to be determined interactively during post-hoc exploration. Due to Cinema's simple file system-based API, it was trivial to hook up the database to Cinema Darkroom and apply different color maps. This example shows a computational fluid dynamic simulation of a jet entering a medium at rest, where the simulation domain consists of a regular grid with two scalar fields, the velocity and vorticity magnitude. During the simulation, we generated a cinema database consisting of two individual cutting planes, a contour, and streamlines that were seated on the contour. If a cinema database contains depth buffers of individual objects, as in this case, then it is possible to dynamically compose them post hoc, where the user can control via the shader network which elements are shown and how they should be colored. If we additionally know the camera calibration that was used to generate a G-buffer, in other words, the position, orientation, and view box of the camera, then we can actually recompute the 3D world location of each pixel. Here, in this example that shows a contour of the entropy field of the Richtmeier-Meshkov instability, we recomputed the 3D location of every pixel that depicts the contour and color the pixel by its world Z coordinate. So this height field was not stored in the cinema database, it was reconstructed post hoc. This can even be used to project new geometry into image space. In this example, we computed at simulation runtime via TTK the location of persistent maxima of the height field defined on the contour. This list of point locations was then used during post hoc analysis to project spheres into a new depth buffer, which was then correctly composed together with the depth buffer of the contour. To correctly perceive 3D datasets, the human visual system needs depth cues, most importantly in the form of shadows. However, correctly lighting a scene is very tricky, even if one can perform the complete rendering interactively on a desktop machine. In recent years, path tracing techniques have been established as an excellent tool to light a scene, especially in the context of scientific visualization. However, path tracing still requires correctly positioning light sources and tweaking parameters such as the exposure and ambient occlusion factors. One also has to take care that the lighting doesn't interfere with the expressiveness of the visualization, by for example darkening regions that contain important scalar field information. Getting good results usually involves interactive exploration, which we simply cannot do in situ use cases. With deferred rendering, however, we can adjust lighting interactively during post-hoc exploration by using techniques such as screen space ambient occlusion and screen space depth darkening. These techniques, of course, only approximate global illumination, but they can still achieve excellent results, and they enable illustrative effects that cannot be achieved with conventional path tracing, while requiring much less computational effort. The scene shown on this slide consists of complex streamline geometries, which are shaded via the same SSAO technique, but at 3 different sampling radii, which are specified in % of the image height. As you can see, small radii highlight local details, while large radii approximate lighting more globally. This radius can be adjusted interactively in Cinema Darkroom based on the visualization task at hand, and it is even possible to combine different SSAO outputs in the node editor to combine shading at different scales. However, SSAO of course also has its limitations. The current SSAO technique used in Cinema Darkroom is optimized for surface-like objects. This technique still works well for the streamline example, but fails to produce adequate depth cues for scenes with high varying depth buffer values, such as the ones that occur in particle visualizations. In the future, we plan to integrate SSAO techniques that were specifically developed for such visualizations. In this final example, I want to highlight again the quality of visualizations that we can get out of a deferred rendering pipeline. Here you can see a porous limestone ground sample taken from South Florida, as well as the path of water as it would run through the cavities of the stone. The stone is colored according to its height, and the water path is shown via blue streamlines. Currently, the entire shading is done again via SSAO, which doesn't do a bad job, but it's still hard to notice details, the spatial relationship between streamlines, and the structure of the stone. By additionally applying image-based silhouettes, perception improves drastically, as edge highlights help us to recognize shapes and their spatial arrangement. Spatial perception can be improved even further via screen space depth of field, although we recognize that it is a controversial effect. But if used correctly, it is our belief that it can greatly improve the quality of visualizations by automatically highlighting a part of the scene while still providing context. Like in this example, it nicely highlights the tips of the streamlines and creates the illusion that the streamlines are coming towards the observer. In conclusion, we describe a deferred rendering framework for high-quality visualization of datasets of any size. In the context of in-situ visualization, our framework can be used for interactive post-hoc visualization based on a cinema database that has been generated at simulation runtime. In the future, we plan to integrate more image-based shading techniques, and it is our hope that Cinema Darkroom can establish itself as a unified benchmark environment for post-hoc visualization, where the research community can easily contribute new techniques and compare against existing approaches. However, CT is currently limited to G-buffers that depict fully opaque geometry. This notably excludes post-hoc volume rendering, except in its most basic form of directly storing colored images in the cinema database. Of course, we are also working on the ParaView integration, and I hope that at the time of the VIS conference, there already exists a ParaView discourse thread that pushes the development of the node editor and Cinema Darkroom forward. So where can you get Cinema Darkroom? At the time I recorded this video, the plan is to ship it together with the topology toolkit, since TTK already has a powerful cinema adapter. But as teased before, we are also trying to ship it as a standalone plugin to make it more accessible. So please check out my webpage, the TTK webpage, and the ParaView discourse channel on any updates. Of course, I'm also happy to answer any questions, and if you want to get involved, please contact me. This concludes my talk, and I thank you all for your attention. Goodbye.